And finally, wrapping up lesson 16.5, the reason for the name divergence, when we take the divergence of a vector field, is understood in the context of fluid flow, and in particular as a rate of change. If your vector field is measuring the velocity of a fluid or a gas, then the divergence of that vector field represents the net rate of change with respect to time of the mass of the fluid or the gas flowing from that point x, y, z. Okay, so we also want to talk about another differential operator that can occur. What if we took the divergence of the gradient of f? Well, we can see that if we were to apply via the dot product del about the gradient of f as a dot product, very quickly I think it becomes pretty evident that we'd wind up just with a second derivative of f with respect to each of the three variables. Second partial derivative of f with respect to x, plus second derivative of f with respect to y, plus the second derivative of f with respect to z. Once again, this quantity is not a vector itself, it's a scalar. And it shows up so much that we can abbreviate it as del squared of f. This operator, del squared, is also known as the Laplace operator. And the Laplace operator shows up in later courses. The author is really just introducing it here. We're not going to be discussing it at great length. But finally, the curl and divergence operators that we've just talked about can allow us to rewrite Green's theorem in versions that will help us out later as we go to the end of chapter 16. Green's theorem was what we looked at extensively in section 16.4. It linked a line integral with a double integral. And what we have right here, a very similar fashion to what we did last section, is that when we were evaluating this line integral, of course moving in a positive oriented direction, we were evaluating work. We saw that that could be done, and we were working off of a tangent component. Now, as we're looking at this first part of Green's theorem, we can look at the curl of f dot k, and if that's the case, we would effectively arrive at Green's theorem. That might seem, dare I say, even rather strange right now. Let's go back to the beginning of the notes to see that. If we went right back to the very beginning of the curl, imagine that we were dotting that with a vector k, and not to mix notations here, but let's say that I just used a bracket. Vector k, of course, could be thought of as 0i plus 0j plus 1k. Imagine that we were doing a dot product. Well, look, the I component in the curl would wipe out as it was multiplied to 0. Likewise with the j component, multiplied to 0 as well. But look at our last part of the dot product. 1 for the k, 1k, times partial derivative of q with respect to x minus the partial derivative of p with respect to y. Well, my goodness, what we saw in that last section, if you really think about it, was this double integral where we had partial derivative of q with respect to x minus the partial derivative of p with respect to y. And what I just showed you a moment ago was that when you write curl of f dot k, my goodness, we arrive at what we saw last section. We just saw that going back to the top of the notes. Again, that is working through the tangent component of this vector, or of a vector drawn in this vector field. So as we look at another way of evaluating Green's theorem, well, the author makes a big to-do proving this out step by step. And I just want to introduce it. We will discuss this at length later on. Just like earlier in the year, we looked at the acceleration vector in terms of components, in terms of a tangent component and a normal component. And that very often can be very helpful and useful. Well, imagine that you evaluated the work done on this path, but in the direction of the normal vector. And again, F dot n, remember force dot a distance here. Imagine that we were evaluating it in that regard. It can be shown that that plain and simply would be the divergence of vector field F. I'm not going to prove that right now. The author does write it out extensively in the book, but think of this as a nice introduction. It will prove very helpful as we get into later sections of chapter 16. Okay, we'll have a wonderful break. We'll be picking up chapter 16 in January, finishing it all up. Hope you get a lot of rest and this lesson's making sense. Best of luck to everybody.